Up until this point in the year, we've dealt with forces that exist between objects that are in contact with each other. They push, they pull, they rub on each other. It's not hard to see where the force comes from. The forces we're going to be most interested in for the rest of the year aren't like that. In fact, they can act at a distance. I'll give you an example. Here's the Earth. We know the sun is very far away from it. And yet the sun is what's making the Earth orbit, go in a circle. How's it doing that? We know electrical charges put forces on things. Protons push on each other. They pull electrons. There must be some force acting across this distance, and it's those kind of forces we're now interested in. So, if we talk about the force of gravity in particular, it seems to have a pattern around the Earth. I'm sitting here in Connecticut, United States, and the force of gravity on me is down. Somebody in India, the force of gravity would be down. Someone in Australia, the force of gravity would be down. Someone in Bolivia, it would be down. But for all of us, down is different. Because really, down for all of us is pointing in towards the center of the Earth. So we know that the force of gravity varies around the Earth, but it's always directed inward. What's the difference between the force of gravity here, or here, or here? We know gravity exists in those places. But is it the same? Is it different? That's what this unit and this lecture is supposed to be about. So, it was figured out over a large period of time, from the 1300s all the way up through the 1600s, that gravity, static electricity, and a bunch of other things spread out from their source in a very particular pattern. And that pattern is known as the inverse square law. The easiest way to see it is to imagine throwing a rock onto a very still lake. So let's do that. All right, so I'm going to throw this rock into the water, and I want you to watch the pattern that the waves make. So as you can see, they're circular, they're spreading out, and as they get farther and farther away, they seem like they dissipate. And that's because they're spreading out over larger and larger space. All right, so I hope you saw what those waves did. They started to spread out. In larger and larger and larger concentric circles. And the waves were very large near where the rock went in, but their energy spread out over larger and larger and larger circles, and therefore the waves weren't as high the farther and farther away you got. It's like they dissipated over a larger and larger space. That idea is the big idea on how gravity, electricity, and some other things like light spread out. Let's look at the force of gravity, for example. We're going to see that gravity is caused by things that have mass. So we've got the Earth in the middle of this sphere. So this imaginary sphere on the outside, which usually gets used to teach astronomy, imagine we were standing on it. The Earth is pulling on me, and it's pulling, or it could be pulling, on an infinite number of other people all around this plastic sphere who are the same distance from the sphere as I am. Now, imagine the sphere got twice as big. There's so much more surface area now for people to stand on. Each of them would still get gravity from the Earth, but it would be a diluted gravity. The gravity would have diluted because it would have spread out, just like the waves from that rock being thrown in the water spread out. So, if you think about what I'm talking about, this is area. I'm running my hands over it. We could tile this with floor tiles that have length times width. So, as you get farther and farther away from the center of that sphere, the surface area of the imaginary sphere you're standing on gets bigger. What surface area? Well, for a sphere, it's 4 pi r squared. So as you move a distance r from the center, gravity spreads out by a factor of some number times r squared. So if spreading out an effect, whether it's gravity, light, radioactivity, if spreading it out over more area dilutes it, we expect an inverse relationship. What I see here is Fg is proportional to 1 over distance squared. In other words, as area, which is measured in square meters, square inches, square miles, whatever, gets bigger, any place has less of that thing. Now the distance we use in calculating the surface area of a sphere is the radius. So what we're proposing is that as we get to bigger and bigger radii, the effects of all these things get diluted. Now, this was known to happen for light. There was a lot of debate in the late 1600s whether this happened for gravity. And I want to first demonstrate that it actually does happen for light. Then we're going to kind of look at some 20th century physics, and we're going to look that it also happens for nuclear radiation. And later we'll return and talk about how Isaac Newton experimentally showed in the 1600s that it also happens for gravity. Let's start by seeing how light spreads out. Light's going to seem brightest close to a candle. As we get to larger and larger radiuses, it's spreading out over larger and larger surface areas. Again, surface areas that look like this sphere. And that means each location appears to be getting a dimmer light. So let's test that. This box is a really cool device for measuring the relative intensity of two light sources. I'm going to light these two candles. I'm going to light this one here. And I'm going to put them into the box. And as you can see, there's a device here that slides up and down. And what this lets us do is it lets us find a balance point for where the light from the two candles appears to be just as intense as the light from the one candle. Now obviously we have to do this in the dark to get any sort of meaningful result. So what you'll be seeing here is a screen with a cutout on it. And there's two mirrors in the back that enable us to observe both sides of the screen. On each side facing a candle, there's an opaque part that doesn't let light through, and there's a translucent star that does let light through. This enables moving the whole screen back and forth to get the exact same light intensity on both sides. Let's see how that works. And what we're looking for is the place where the light balances. We can tell if the light's balanced by looking at the little window that's shaped like a star. You look for when the window has the same brightness as the surrounding circle. And you want that to be true on both sides. So we found it for here. And that's at about 58.3 centimeters. So you can see that right here. Actually 58.8. So let's check and see if this balance point has any sort of useful information about how light spread out from our twice as bright source from our half as bright source. Oh, I forgot, safety is important. So anyway, you can envision that light is spreading out from this source in spheres. So anyway, if light spreads out according to this inverse square law, then we expect there to be a relationship between how far we are from our twice as bright candles and how far we are from our half as bright candles. So let's try to use this law to predict where that space will be and see if it actually corresponds to the 58.8 centimeters we found. Other thing we need is that this is actually 0.588 meters and that the entire distance was 1 meter. So let's predict where the spot should be, where our brightness should be equal. So we're going to say our two candles. We want to find out what distance r from them, the brightness from one candle is the same. So we don't know what r is, but we're proposing this inverse square law because we expect it has spread out over a larger and larger area. We don't know what the relationship between, we don't know how far this distance is either, but we do know the whole thing was 1 meter. And that therefore, the distance from our two candles has to add to the distance from our one candle to give us 1. So those are both squared. I'll spare you the math, but I just squared that binomial. I cross-multiplied to get this, and I got this equation here, 2 minus 4r plus r squared is 0. Did the quadratic equation, and I got two answers, but only one of them makes sense, 0.586 meters. The other one is outside the box, basically. It's 3 meters down. But it's very close to what we actually measured. So I hope I've now convinced you that light spreads out according to the inverse square law. The bigger radius you have, the more diluted light is. We've shown that quantitatively. We can also show this quantitatively for another phenomenon, which is nuclear radiation. We're going to look how gamma rays from a radioactive source spread out, and we'll see if that follows the inverse square law. Ironically, this demonstration is almost identical to the candlelight one you just saw, because gamma rays are a form of light, just a more dangerous one. Let's take a look. These are two radioactive sources made for school use. The top one is polonium-210. It emits alpha particles, and the bottom one is cobalt-60, which emits gamma radiation. We're going to use the cobalt-60 because this is a pretty old sample, and I don't think the PO-210 is any good. Also, this kind of Geiger counter can't measure radiation that consists of alpha particles. So this is a Geiger counter. This particular one is somewhat ominous looking because it's a Cold War era relic. The CD is for civil defense, so this was made for first responders to use in case of nuclear attack. But it's a good way of measuring whether something has radiation. There's two scales on the meter, and the one we're interested in is the bottom one, which is CPM, which stands for counts per minute. So this is 0, 100, 200, 300. It's not very linear because they have the top of the scale, milliroentgens per hour, set up to be linear. There's lots of different units for measuring radiation exposure. It's more complicated than we need to go into here. So we're going to use this to demonstrate the inverse square law in a slightly different way. Okay, so we're going to bring our source close to the Geiger-Müller tube, and we'll just kind of find where I can move this to get the most reading. All right, so that seems to be our peak. And that's right like this. So I have the GM tube. I have it right on the 3 centimeter mark. So at this source, a centimeter away from the tube, I'm getting a maximum of about 150 counts per minute. Let's go 2 centimeters from the tube. I'm getting a maximum of 50 counts per minute. We'll go 3 centimeters from the tube. I'm now kind of barely registering, maybe around 25, as high as like 35. Let's crunch those numbers and see if there's any pattern to them. So I put these numbers into this table. These are the numbers I measured in the previous videos. And I'm using Professor Eric Rogers' strategy for doing a quick check of the inverse square law. This is from his famous Coulomb's law video. And basically what you do is you assume the inverse square law is true, in which case we should be getting a fourth of the effect when we double the distance, and a ninth of the effect when we triple the distance. And you can see those numbers match, I would say, fairly closely. There's definitely some experimental error here, but this does seem to support the idea that gamma radiation spreads out according to the inverse square law. So here's the cross-section of the spheres over which the gamma radiation is spreading out from the source. Again, this is an important law of nature when things spread out from a point source. We see it over and over again. The inverse square law has important implications for keeping people safe from radiation. As we move farther away from the source, the effect of the source is spread out over more and more area. That means you receive less and less dose the farther away you get. This is why nuclear plant boundaries are set up the way they are, to keep the public sufficiently away from the reactors, which lowers their dose. This is also why when they built the new arch over the ruined Chernobyl reactor in Ukraine, they actually built it at a distance away from the reactor and rolled it into place. Had they tried to build it on top of the ruined reactor, people would have been too close to the source. But by getting farther away, the exposure could be low enough to protect the workers.
We've now seen that the inverse square law governs anything spreading out from a point source. We've seen it works for both light and nuclear radiation. Later in the class, you'll see Professor Eric Rogers demonstrate pretty simply that it works for the electrostatic force too. But how did Isaac Newton show in the 1600s that it works for gravity? That's pretty impressive. If we want to actually show that, we would have to take measurements relatively close to the Earth and relatively far away. How do you do that without going into outer space?
On Earth, we know that the acceleration of gravity is g, which on Earth is 9.8 meters per second squared. What if you go away from Earth? Like, say, out to the moon? What's the acceleration of gravity out there? Well, we know that the moon has the force of gravity acting on it. We know that it's moving in a circle. So can we figure out from those two pieces of information whether the acceleration of gravity has diminished out there? Something that would help us see that the inverse square law is true? Well, we can, if we consider it a circular motion problem. We write sigma f is ma. We don't know the mass of the moon, but it doesn't matter because we know that the only force is the force of gravity. And what is A if we're moving in a circle? Well, of course, it's v squared over r. What's the force of gravity? Well, it's m times whatever the acceleration of gravity is out there. So, can we find out what the acceleration of gravity is out there? Absolutely. We don't even need to know the mass of the moon. What we're going to do is we're going to step-by-step figure out what the velocity of the moon is, and then figure out its distance from Earth. So, as far as the velocity, we know that the velocity equals distance divided by time. And if you're moving in an orbit around the Earth, the distance of an orbit is the thing's circumference, and the time is the period, or how long it takes to do a complete cycle.
We know about the period of the moon going around the Earth. It's a month, and a month on average is 27.3 days for the moon to completely come back. So here is me taking the 27.3 days and converting that into seconds. And then I'm doing the circumference over time equation equals velocity. So I get that the moon's velocity is a little more than 1,000 meters per second. And then plugging into g is v squared over r, we end up having the Earth's acceleration of gravity as far away from the Earth as the moon is really small. It's about 0.003 meters per second squared. So gravity definitely decreases as you get farther away. And Newton was wise enough to realize that he could see that just by looking at how the moon moved. And that's why he gets the credit for discovering this rather than Robert Hooke. So what Newton was interested in was not so much what the value for gravity as far away from Earth as the moon is. He was interested in how many times smaller it was than on Earth. And what he knew was that if you were standing on the surface of the Earth, your distance from the center is 60 times smaller than the distance of the moon from the center. The moon is 60 times farther away from Earth than you are. But if you divide this 0.00272 meters per second squared by the 9.8 meters per second squared you're experiencing as the acceleration of gravity, you see that it's about 3,600 times smaller. What relationship do 60 and 3,600 have? They're 3,600 is the square of 60. So you got 60 times farther away. Gravity decreased by 3,600. So that was how Isaac Newton showed that gravity decreased just like light does according to the inverse square law. He had to measure something far from the Earth and something close to the Earth. He compared their accelerations of gravity. We've spent a lot of time harping on this point, that things that spread out from a point source dissipate according to the inverse square law. You've now seen this experimentally shown for light, for nuclear radiation, and now Newton's using the moon's motion to show it for gravity. What we need to do now is really talk more about the force of gravity, but we will revisit the inverse square law later when we talk about another force that spreads out from a point source, the force involved with static electricity.